In this video, we'll be looking at doing a quick introduction to acids and bases. So the first thing we want to do when talking about acids and bases is being able to identify some general characteristics about each. So we want to talk about what actually goes into making an acid an acid. And when we talk about acids, what we want to think about is acids are going to generate H plus ions in solution. And we can identify acids a lot of times just by looking at the formula. When we look at the formula for an acid, it'll often lead with an H in the formula. So you'll have H, and then you'll kind of have the rest of the elements that are in that acid. So that's what we mean when we say leads with an H. And when we look at some specific examples of acids, you're going to see that they're all going to lead with an H. We're familiar with some of the properties of acids. Depending upon the acid and the concentration, they can be quite caustic and corrosive. We're also familiar with some of the acids in our foods. Generally, things that are sour tasting to us, things like lemon juice and vinegar, are sour because those things are very acidic. Even things that we don't normally associate as being extremely sour, like lemon juice or vinegar, still could be very acidic though. Something like orange juice isn't nearly as sour as lemon juice, and it's not quite acidic, but orange juice is still pretty acidic. The difference between orange juice and lemon juice is that orange juice has a lot of sugar in it that is masking some of that sour taste coming from those acids. We're going to see that acids come in two different types, strong and weak, and we want to associate those the exact same way we did strong and weak electrolytes. So the first type of acid that we want to talk about are the strong acids. And strong acids, just like strong electrolytes, will completely break up into ions. And one of the ions that they break up into is going to be those H plus ions. There are only 6 strong acids. If it's not on the list on the right, you want to assume that it's not strong. So on the right-hand table, kind of boxed in red right now, are a list of the names and the formulas of the 6 strong acids. You want to memorize these. And the reason why you want to memorize these, both in terms of names and formulas, is that there are millions upon millions of different acids, but we only have these 6 strong ones. So if you know the 6 strong ones, then you know any acid that's not on this list is not going to be strong. It's going to be one of the weak acids. So the best way to deal with these is to flashcard them. So on one side of your flashcard, you want to put the name, the other side the formula, and you want to have these 6 strong acids memorized. So strong acids are going to break up just like the strong electrolytes do. They're going to completely break up into ions when you place them in water. So one of the acids on our list, HBr, when we would place that into water, is going to completely break up into H plus and Br minus ions. You can see that with the single-headed arrow showing that it's going in one direction. So these strong acids are going to produce a lot of ions. If you started with 100 units of HBr, all 100 units of them are going to break up into 100 H plus units and 100 Br minus units. You have that complete breakup, you're going to produce a lot of H plus ions from these strong acids. Any acid that's not in our list of strong acids are weak acids. So that's why it's so important to memorize those strong acids. Any acid that is not a strong acid, we want to identify as a weak acid. That's why it's really important that you memorize the strong acids, because everything else not on that list will automatically be weak. And what we're seeing with our weak acids is something very similar to weak electrolytes. These will partially break up into ions. We've actually already seen an example of a weak acid. When we talked about weak electrolytes, we used HF as an example. Well, not only is HF a weak electrolyte, it's also a weak acid because one of the ions that it's breaking up into are these H plus ions. So it's going to partially break up into H plus and F minus ions, but notice again, we see the double-headed arrow that's highlighted in green. Remember what this double-headed arrow is showing you. The double-headed arrow shows only a partial breakup into ions. Remember, this partial breakup heavily favors the side with no ions, such that if you started with 100 units of HF, only about 2 or 3 of those are going to break up. So that means if you started with 100 units of HF ions, 100 units of HF, you may get 2 or 3 units of H plus and F minus. You only get a small amount of those ions coming out. That's what makes these weak acids. So now we want to look a little bit at the general characteristics of bases. What all bases have in common is that bases are going to generate hydroxide ions, that OH minus ion. Another way of looking at bases, though, is how they're related to acids. Bases end up being the exact opposite of acids. So being acids generate H plus ions, what bases are going to do are absorb H plus ions. So you can either think about bases as generating hydroxide ions or as absorbing H plus ions. Just like acids came in strong and weak varieties, our bases are going to come in strong and weak varieties as well. Bases can also be caustic and corrosive. You're probably most familiar with bases in terms of their physical property of being slippery. Most of your things that are basic have that slippery or slick feel to them. Things like soaps, shampoos, detergents, cleansing agents that have that slippery feel are slippery because of the bases in them. Additionally, bases can also be bitter tasting. So when you think about this, you may want to think about dark chocolate. Dark chocolate has very little sugar in it to mask the bitterness. Some of that bitterness is the result of the bases that exist in that dark chocolate. Our first type of base that we want to talk about are the strong bases. So strong bases, just like strong electrolytes, strong acids, completely break up. So these are going to completely break up to directly produce these hydroxide ions. We can think of these as ionic hydroxides. And we don't really need to memorize a list. Any ionic compound that dissolves and has the hydroxide ion in it is a strong base. So if you have an ionic compound that has hydroxide in it and it dissolves, well, you're directly producing a lot of hydroxide ions. So just some examples of these ionic hydroxides, things like sodium hydroxide, potassium hydroxide, barium hydroxide. These work the same way that a strong electrolyte would work. We take an example of a strong base, KOH. Well, even before we did acids and bases, you would at least recognize this as a strong electrolyte because it's going to break up into ions completely. Well, not only is it going to break up into ions completely, one of those ions is the hydroxide ion, which is what makes it be a base. So when you put potassium hydroxide in water, it's an ionic compound. It will completely split up into ions. You'll get your potassium ions dissolved in the water, and you'll get your hydroxide ions dissolved in the water. And again, notice the arrow. It's a single-headed arrow saying that that is going to completely break up into ions. So if we think about this, if we started with 100 units of potassium hydroxide, all 100 units of that potassium hydroxide are going to break up, giving you 100 potassium ions and 100 hydroxide ions. You get that complete and total breakup to directly produce a large amount of hydroxide ions. That's what makes these strong. we kind of compare that to weak bases. So when we think about weak bases, our weak bases work by a different mechanism. Weak bases are going to produce hydroxide ions indirectly. You won't see the hydroxide ion directly in the formula of a weak base. They do it through a reaction with water that we're going to see. Because of this indirectly producing hydroxide ions, these can be tough to identify, but we're going to show you a way of identifying these weak bases. So one example of a weak base would be fluoride ion, F-. So fluoride ion is a weak base. Notice you don't see hydroxide ion anywhere in the formula. And we're going to show you how you could identify fluoride ion as a weak base, but first let's look and see how it reacts. Fluoride ion works as a weak base by producing hydroxide ions indirectly through a reaction with water. And what ends up happening is fluoride ion is going to grab an H plus from the water. If fluoride ion grabs an H plus from water, well, fluoride ion picks up a H plus, that's going to make HF, and then what's left behind from the water? So fluoride ion came in and grabbed an H plus from water. So water lost an H plus in this. Well, if water lost an H plus, what you would have, highlighted in green, would be hydroxide ion. So that's what ends up happening. Fluoride ion grabs an H plus from water to create that hydroxide ion. And notice your arrows again. Your arrows are double-headed arrows, identifying this as a weak reaction, as not going to completion, such that if you had 100 units of F minus, maybe only 2 or 3 actually react with water to give you only a couple units of hydroxide ion coming out. So because you don't see hydroxide ion directly in the formula of these weak bases, they can be very, very challenging to identify. So being they're difficult to identify, we want to show you a technique to identify them. And they're going to be identified through what we call conjugates. We're going to talk about that on the next slide. But I want to show you the mechanism of how these weak bases operate. By grabbing an H plus from the water, what happens in that process is what's left behind after the F minus has grabbed an H plus from the water. Water is going to lose that H plus. That's how your hydroxide ion gets created. So we want to look at the idea of conjugates. And what conjugates are a pair of molecules who are related through the presence or the absence of H plus. That's the difference. In this pair of molecules, one of them will have the H plus, one of them will not have the H plus. So some examples of some conjugate pairs. HCl and Cl minus. If you look at HCl and Cl minus, the HCl has the H plus, the Cl minus doesn't. They're a conjugate pair. We look at the next pairing, HF and F minus. HF has an H plus on it, F minus does not. Those would be a conjugate pair. Next example, HNO2 has an H plus, NO2 minus does not have an H plus. So conjugates are these pairs of molecules where one has the H plus, one of them doesn't. And we use this relationship through the conjugates in order to correctly identify when something is a weak base. And here's how that works. Weak bases are the conjugates of weak acids. So we said we had a tough time identifying weak bases, but we have a much easier time identifying weak acids. So we're going to use the relationship of conjugates to identify what the conjugates are and then figure out what we have. If we can identify something as a weak acid, then we know automatically its conjugate is a weak base. So we're using something we have an easier time identifying to help us with something that we have a more difficult time identifying. So let's kind of look at how this works. We're trying to figure out what's going on with F minus. The conjugate of F minus is HF. Remember, we already saw them as a conjugate pair already. One has the H plus, one does not have the H plus. We can already identify HF as a weak acid. How do we know it's a weak acid? We know it's a weak acid because we can identify it as an acid and it's not on that list of the 6 strong acids. So we instantly know HF is a weak acid. Now, through its relationship to F minus, them being conjugates, since we can identify HF as a weak acid, we know F minus is going to be a weak base. The conjugate of a weak acid will be a weak base. And that's the technique you're going to use to identify these weak bases. And we might be thinking about, okay, we have conjugates for weak acids, weak bases. Well, what would the conjugate of a strong acid be? Now, initially we might think, oh, the conjugate of a strong acid is probably going to be a strong base or a weak base, but that's not true. The conjugate of a strong acid does not have any acid-base properties. So the conjugate of a strong acid is not an acid or a base, and we want to look at this. If we look at an example of a strong acid, an example of a strong acid would be something like HBr. Well, what's the conjugate of HBr? The conjugate of HBr would be Br minus. But when we think about something as a strong acid, notice the arrow. Arrow is just pointing to the right, meaning complete breakup in the ions. Remember what it means to be a base. For a base, something has to be able to grab H+. Look at the arrow. There's no arrow going to the left. Can Br re-grab that H+ ever? No. If Br can't grab an H+, it's not going to be able to function as a base. So the conjugate of a strong acid is nothing. It does not have acid-base properties. The conjugate of a weak acid is a weak base. So here we want to do an example problem that kind of illustrates how we're going to identify things as acids or bases and whether they're going to be strong acids or weak acids, or strong bases, weak bases, or if they don't have any acid-base properties at all. So the first one we want to look at is calcium hydroxide, CaOH2. So right away we want to think, what do we see in that formula? Well, right away in that formula we see that polyatomic OH, that hydroxide ion. So we want to think, we're already thinking it's going to be a base. Is this an ionic hydroxide that's going to completely break up into ions? Well, absolutely. We think about what makes up calcium hydroxide. We're going to have calcium plus 2 ions along with a couple hydroxide ions. So right away we can identify this one as a strong base. SB for strong base. Calcium hydroxide is going to be a strong base. If we look at the next one, HClO3. Well, right away, looking at the formula, we're thinking probably going to be an acid. Why? It's leading with an H. We see leading with that H. So we're thinking acid. Now we have to ask ourselves, is that one of the list on the list of the strong acids, or is that going to be a weak acid? So if we look at the formula very carefully, we would see it's not on that list of the strong acids. So being it's not on the list of the strong acids, this has to be a weak acid. So WA for weak acid. We look at the next compound. Our next compound is bromide ion, Br minus. So here, if we kind of go through our list of what we have, is it an acid? Well, I don't see an H anywhere in the formula, so probably not an acid. Do we see any ionic hydroxide in there that would make it a strong base? No, we definitely don't see hydroxide ion. So being we don't see hydroxide ion, we can eliminate strong base. Now we're left with 2. This could either be a weak base or it could have no acid-base properties. And these are always going to be the toughest decisions to make. Is it a weak base or does it not have any acid-base properties? the only way to look at this is to look at its conjugate. So if we think about bromide ion, what's the conjugate for bromide ion? The conjugate for bromide ion is HBr. So now by identifying bromide ion's conjugate, we can figure out what bromide ion is. So bromide ion's conjugate is HBr. What type of acid is HBr? HBr is a strong acid. So being HBr is a strong acid, the conjugate of that strong acid, which is Br minus, is not going to have any acid-base properties. The conjugate of a strong acid is nothing. So this would be no acid-base properties for bromide ion. It's not an acid or a base. We look at our next one, H2SO4. Right away we're thinking this is probably an acid because it's leading with an H. Is it going to be a strong acid or is it going to be a weak acid? Here we're thinking about those list of memorized strong acids. Is this one of the ones on the list? The answer is yes. So right away we can say this is strong acid, SA for strong acid. Next, we're looking at cyanide ion, Cn-. So we're kind of going through the list. Is it likely to be an acid? Well, I don't see an H anywhere in the formula, let alone in front, so probably not an acid. Is it a strong base? Is it an ionic hydroxide? No, I don't see any hydroxide ion anywhere in here. So now we're left with our choice between could be a weak base or it could be nothing. So how do we have to analyze that? We have to analyze that by looking at the conjugates. So we have Cn-. What would be the conjugate of Cn-? Well, the conjugate of Cn- would be HCN. So now we're using what we know about conjugates and what we know about HCN to figure out what's going to be going on with Cn-. Well, HCN, what do we know about that? Well, we could identify HCN as a weak acid. How do we know it's a weak acid? Well, it's leading with H, and it's not on the list of the 6 strong acids, so therefore it has to be a weak acid. Now that we know that HCN is a weak acid, we're using that information to determine what's going on with its conjugate. Remember, HCN and Cn- are conjugates. The conjugate of a weak acid is a weak base. So that means Cn- ends up being a weak base. Because HCN is a weak acid, that's how we were able to determine that Cn-, remember that conjugate pair relationship. The conjugate of a weak acid is a weak base. That's what we use to determine that Cn- ends up being a weak base. So what we want to do next is to talk a little bit about the pH scale. So we're not going to do any calculations on the pH scale, but we should understand some key points about the pH scale such that we understand how it works. So the first thing we want to look at for key things to look at on the pH scale is that idea of neutral. We probably recognize that pH 7 is neutral. But what does that really mean? Well, the fact that 7 is neutral, what that really means is we have equal amounts of OH- and H+ in there. We kind of highlight pH 7 on the pH scale, and we look at how much H+ we have and how much OH- we have. You see that we have equal amounts of each, and that's what it really means to be neutral on the pH scale. The other thing we want to look at on the pH scale is that things that are less than 7 are acidic. And what that means is if you're less than 7 on the pH scale, you're going to have greater amounts of H+ than OH-. That's what it really means to be acidic. So if we're looking at the acidic side of the pH scale, if we look at something like pH 4, so if we look at pH 4, Let's look at how much H plus versus OH minus we have. So this is highlighted in green. You can see 0.0001 H plus, but a lot less OH minus, 0.000, a whole bunch of zeros before we hit the 1. You can see you have a lot more H plus than you do OH minus. That's what it means to be acidic. But even when you're acidic, you still have small amounts of hydroxide ion present. It's just you have a much, much smaller amount than H plus, but it still exists in that solution. If we look at what's happening on the pH scale when you are greater than 7. When you are greater than 7 on the pH scale, you're on the basic side of the scale. What that means is you're going to have greater amounts of hydroxide ion than you will H plus. And we can look at that. If you're looking at pH 10 highlighted in blue here on the pH scale, let's look at how much H plus we have and how much OH minus we have. Well, you can see we only have a very, very small amount of H plus, but we have much more OH minus. So when you go to higher numbers on the pH scale, you're on the basic side of the scale. That means more hydroxide, less H plus. But even on that basic end of the scale, there are still small amounts of H plus around. No matter the pH, you will always have some amounts of H plus and some OH minus. It's just a matter of how much. If you're acidic, you're going to have much more H plus than OH minus. If you're basic, you're going to have much more OH minus than H plus. The last thing we want to look at on the pH scale is this idea that it is in a log-based scale. Now, we're not going to do any calculations, but we at least need to understand what a log-based scale is. On a log-based scale, that means every unit change on the pH scale represents a 10-fold change in H plus and OH minus. So if I kind of highlight a couple pHs in orange, if we look at pH 6 compared to pH 7, well, look at the H plus. You kind of move the decimal place, you'd see pH 6 has 10 times more H plus than pH 7. If we look on the OH minus side, pH 6 has 10 times less OH minus than pH 7. So things change by a factor of 10 in that respect. Every pH unit changes things by 10. If you're going to lower pH units, that would be 10 times more acidic, 10 times less basic. If you're going to higher pH units, then you're going to be 10 times more basic, 10 times more OH minus, 10 times less acidic, H plus. And we can see that with some other points that I'm going to highlight on here in red. If I look at pH 8 compared to pH 7, 0.000001 H plus. Okay? Compare that to pH 7, 10 times less acidic. But look at what's happening with the OH minus. Comparing pH 8 to pH 7, pH 8 has 10 times more OH minus. So every time you move one unit on the pH scale, you're changing the amount of H plus and OH minus by a factor of 10. And this is multiplicative, not additive. If you look at the pH scale, one unit gives you a 10-fold change. Changing 2 pH units represents a 100-fold change. Changing 3 pH units, a 1,000-fold change. If we went up to 4 pH units, that would be 10,000. 5 units, 100,000. 6 units, we're looking at a 1,000,000-fold change. It's not 10 plus 10 plus 10, it's 10 times 10 times 10 times 10 times 10. 10, 100, 1,000, 10,000, 100,000. So you get big changes in this. And you can kind of look at this and see this. If you kind of look at the pHs highlighting in purple, 12, 13, and 14. You compare 12 to 14, how much did things change by? Well, 12 to 14 would be 2 pH units. Well, 2 pH units is going to change things by a factor of 100. 10 times 10. 3 units, 1,000. 4 units, 10,000. You get very big changes, and that's what it means to be on a log-based scale. On a log-based scale, every unit actually changes things by a factor of 10. So the next thing we want to do is talk a little bit about buffers, what they are, how they work, and kind of why they are so important. And what buffers are a solution that consists of both a weak acid and its conjugate weak base. You need both of them present to have a buffer. Just one is not a buffer. You need both the weak acid and the weak base present. Well, it's also important that they are both weak. Strong acids and strong bases don't work as buffers. So you need a weak acid and its conjugate weak base in order to have a buffer. And that's what buffers are. And what buffers do is buffers resist changes to the pH of a solution whenever you add an acid or a base to that solution. So they help modulate and regulate the pH. So you don't have wide, extreme changes to the pH. It keeps the pH close to the same level. And this is very important. This is critically important. Buffers are extremely important to life. A typical pH in our cells is anywhere from around 7.35 to 7.45. Even going slightly outside of this range, if you start going just 0.1 outside of this range, you're having serious problems for that cell. Anything outside of about 0.2 from this range, you're looking at almost certain cell death. So buffers are important in order to keep the pH of the cell set at a specific range and not wildly changing. And that's why they're so important. Next, we want to talk about how buffers can achieve this very important job. We talked about what they were with being a conjugate weak acid, conjugate weak base pair. Talked about how important they are. How do they actually perform this job? They're able to perform this job as buffers are able to resist these changes in pH by functioning as sponges. I want you to think about what you use a sponge for. You use a sponge to soak up extra amounts of something. It's absorbing something. Buffers kind of act as sponges. They can absorb small amounts of H plus and small amounts of OH minus. And by absorbing those small amounts of H plus and OH minus, they can keep the pH regular and consistent and not have the pH change very much. Talk just a little bit about how a buffer works, and this diagram is a little bit color coded. What you see kind of in the reddish orange represents acids. What you see in the purple represents bases. So starting in the middle, a buffer starts with equal concentrations of conjugate acid and conjugate base. And that's what you see in the middle. You see equal amounts of the acid in red and the base in purple. What ends up happening is these act sort of like molecular sponges. They can soak up extra H plus or extra OH minus. So if we look going to the left, if you have this buffer and you add H3O plus kind of means the same thing as H plus. So you're adding acid to it. Well, what's going to happen? Adding acid to a solution is going to definitely drop the pH, which we don't want to happen. But buffers can stop that process. Buffers can soak up that extra H plus. And how do they do it? Well, the weak base part of the buffer, that in purple, is going to react and act as a sponge by grabbing that H plus. You can see the amount of purple base on the right kind of went down. You can see this amount here went down. Why? That's what was used as a sponge to soak up that H+. Well, what happened to it? Well, that weak base, by soaking up that H+, turned into the weak acid. That's why you see the amount of the weak acid going up. So what did we essentially do? We absorbed that H+ into our buffer, which helped keep our pH very consistent and unchanging. Now, would the pH change a little bit with this? Yes, but very, very little because of soaking up that H+. If we look at the right-hand side of the diagram, what happens if we would add hydroxide ion as we go to the right and add OH-? Well, if we start adding hydroxide ion, what's going to happen? Well, the pH could potentially go up and go up quite a bit, and that could be a problem. We want to prevent that. But we're in a buffer system, so the buffer is capable of absorbing some of that hydroxide ion. How does it do that? Well, the weak acid part of the buffer can soak up some of that OH-. You can see that kind of on the right-hand side pointing to the red. The weak acid, that amount diminished because what happened to it? It acted as a sponge soaking up that hydroxide ion. In the process of soaking up that hydroxide ion, what happened? That weak acid got converted to a weak base. You can see the amount of that purple weak base kind of going up as you go to the right. So what you essentially did is the buffer, no matter if you're going left or right, was able to soak up that H+ or soak up that OH- to kind of take that addition of H+ or OH- out of the solution to help moderate the pH and keep the pH very, very steady. So the pH would only change a small amount because the buffer dealt with that addition of H+ or OH-, with the weak acid absorbing the hydroxide ion or the weak base absorbing the H+ ion. So the last thing we want to look at for acids and bases are some common reactions that happen with acids and bases, and understanding in these reactions what things are going to react and what is going to be produced as a result of that reaction. So the first reaction we want to talk about is called a neutralization reaction. And in a neutralization reaction, what you have is you will always have an acid reacting with a base. And whenever you have an acid reacting with a base, you will produce two different products. You will always produce water, and you'll also produce a salt. And that doesn't mean it's going to be NaCl. What salt really means is salt is kind of a shorthand chemical slang, a quick way of saying an ionic compound. Salt is kind of a shorthand slang chemical way of saying we're going to produce an ionic compound. So anytime you react an acid with a base, you will always produce a salt and water. So if we would look at a specific example of reacting an acid with a base, well, our acid could be something like HBr. Our base could be something like lithium hydroxide. What are you always going to make? Well, one thing you're always going to make is you're going to make water, kind of highlighted in blue. Well, where did you get that water from? Well, that water is going to come from the H+ from the acid and the OH- that's coming from the base. Which specific salt or ionic compound will you produce? Well, that depends upon exactly what acid or what base you end up using. We end up making lithium bromide here because what are our other pieces? We saw where the H+ and the OH- went. The other pieces, the lithium ion and the bromide ion, are then going to combine to make the lithium bromide to make that salt. So anytime you're reacting an acid with a base, you end up forming a salt and water. Our next reaction is what happens when you react an acid with a metal. And the general framework for what happens when you react an acid with a metal is anytime you react an acid with a metal, you're going to get two products. You're always going to get a salt. Remember, that's just an ionic compound. Salt is that kind of slang phrase for that. And what you'll also produce is hydrogen gas. So whenever an acid and a metal react, you'll end up making salt and hydrogen gas. So if we would look at a specific example of this, we could look at something like HNO3, nitric acid. That would be our acid reacting with a metal. Here we pick potassium. What will we always make? Well, we'll always make hydrogen gas. Hydrogen gas is H2, and then you're always going to make a salt. What salt will you actually make? Well, the salt that you will actually make is going to be based upon the specific metal and the specific acid that you use. Here, because we use potassium as our metal and nitric acid, which has a nitrate ion in it, the ionic compound we're going to produce, that salt, is going to be potassium nitrate as a result of that. If you use a different acid and a different metal, you would get a different salt. If you used HCl and sodium hydroxide, well, then you'd make NaCl for that. Your salt is always just going to be dependent upon which exact acid and which exact metal you use. But one thing you're always going to make is that hydrogen gas. So whenever you react an acid with a metal, your two products will always be a salt and hydrogen gas. The last reaction we want to look at is whenever you react an acid with either a carbonate or a bicarbonate. It's the same basic reaction. We're only going to show one of these though. When you react an acid with a carbonate or a bicarbonate, you're always going to get three products coming out. And the three products you're going to have coming out are always carbon dioxide, water, and a salt. Those are three things you will always make. If we would look at a specific example, here we have hydroiodic acid reacting with the sodium hydrogen carbonate. So here in this reaction, what are we always going to make? Well, we're always going to make CO2. That's never going to change. Carbon dioxide is always CO2. We're always going to make water. Water is always going to be H2O. The specific salt that you're going to make, though, is going to be based upon exactly which acid and which carbonate or bicarbonate you are actually reacting. Here we have sodium hydrogen carbonate or sodium bicarbonate, so we can see the sodium ion, and HI, we can see the iodide ion. So when we would pair those up, what salt will we make? Sodium iodide. So whenever you are looking at a acid reacting with a carbonate or a bicarbonate, you're always going to get three specific products. You're always going to get carbon dioxide, you're always going to get water, and then you'll always produce some sort of salt. Remember, salt is just slang for that kind of some ionic compound.